Hello, everyone, and welcome to the Mars Society's third annual International Mission to Mars Engineering Design Contest for high school students. Today, we are in part 3 of the competition, the defense. So each team will have a chance to defend the critiques from part 2, which you can go and watch that video. I would like the students to know that please speak kindly, slowly, and clearly. These are never personal attacks, so please make sure that we keep that in mind when we go throughout today's session. You will have 30 minutes to defend the critiques. You will then get a 2-minute stretch break, and then we'll return for the next team. The final draft of the paper, as a reminder, the final draft for publication, the draft you sent me is what will be graded. The final draft for publication has to be formatted in a certain way to go for publication. And please use the highest resolution images that you have for publication. And make sure we are kind. And next, we will have Team AstroMineX. You will be up first. Team AstroMineX, you have the floor. You may share your screen.
Thank you very much. So we are Team AstroMineX, and today we will defend the critiques that we have received 2 days ago. My name is Matei, and next to me is Teodora.
First, we will talk about the introduction. To effectively address Aspera's feedback, we've transcribed their comments from the second presentation recording. We will address each point in the order raised. First, we will talk about objectives. Let's talk about the fact that we argue that our mission objective of resource extraction is both scientifically and practically justified. While the Viking missions were groundbreaking in shaping our research for life, the lessons learned also highlight the importance of a multifaceted approach to Mars exploration. Resource extraction is critical for the sustainability of any kind of human missions, as it enables in situ resource utilization, reducing dependency on Earth. This supports long-term human presence and further exploration. Moreover, resource extraction missions inherently advance our understanding of Martian geology, climatology, and even astrobiology. For instance, finding and utilizing water ice informs us about Mars's climatic history and potential for past life. Resource extraction missions can enhance our understanding of Mars geology, as locating and extracting resources requires extensive geological analysis. A resource extraction is not mutually exclusive with other scientific objectives like the ones mentioned before. Just because we are focusing on research extraction doesn't mean that our mission cannot provide valuable insights regarding the other topics. We have decided to pursue resource extraction because we found it as the best option on the list of exploration possibilities provided in the official rubric. The reasons are already clearly stated in our final report at page 2, objectives. Therefore, our choice of resource extraction as a mission objective is not only justified, but essential for sustainable and comprehensive approach to Mars exploration. It aligns with historical precedents of exploration driven by resource potential and supports future missions that aim to make Mars a viable destination for human presence. Now we will talk about the objectives regarding asteroid mining. Regarding the statement that asteroid mining could lead to unintended consequences on the Martian environment, potentially bringing contaminants to Mars and putting future colonies at risk, We acknowledge the importance of these concerns. However, our proposal, which is mentioned on page 2 objectives of mining asteroids from the asteroid belt, which is approximately 0.5 astronomical units, or around 75 million kilometers from Mars, incorporates rigorous sterilization protocols and containment measures to prevent contamination, as outlined in existing planetary protection policies. While developing new technologies for resource extraction in microgravity and managing the logistics of material transport are complex, they are within reach given current advancements in space capabilities. We must remind you that the Wrangler systems have a mid to high TRL, and that is without the improvements we proposed. Our approach is not intended to replace scientific exploration on Mars, but to complement it by securing essential resources in a way that minimizes environmental impact on the planet itself. This strategy ensures that Mars remains pristine for ongoing future studies while providing the necessary resources to support a sustainable human presence, thus balancing responsible innovation with economic sustainability. We kept in mind not to put all your eggs in one basket when developing the energy generation systems, the communication systems, and the transportation strategies. Up next, we have the crew selection criteria. You have stated that the paramedic/astrobiologist will only have basic training. Such a thing is never mentioned in our reports. Page 2, crew members. We carefully chose a broad team of 6 specialists. Page 3, crew selections criteria. Each member has undergone rigorous training in their respective fields. The mental health support can also be managed with help of a team of psychologists from Earth with whom we can communicate thanks to our well-thought communication system. We have mentioned at page 3, crew selection criteria, that it is equally important that all crew members possess a general understanding of various tasks and can step in to support each other as needed. That ensures that our medic is still able to support the mission even when nobody is sick or having any kind of mental distress, something your medic does not. Regarding the multiple hats concern, if you are not choosing the best of the best multi-qualified people now when preparing for the most important space mission to date, when will you? You also mentioned that there is no clear chain of command. A leader can only be chosen by their leadership skills and by no means solely by their profession. We are talking about hypothetical people, which we know nothing about except for occupation. For that reason, we have critiqued your decision of appointing the engineer as the team commander. As for our project, the leader shall be appointed after the rigorous training mentioned at page 3 and 4 crew selection criteria.
Now I will talk about the water and oxygen concern. You have assumed that the plan is to rely on a week's worth of water and oxygen until life support systems are established on Mars. This was mostly a misunderstanding of our statements. First of all, we are bringing 500 liters of liquid oxygen as stated at page 22, table 5, cargo weight distribution. Knowing the density of liquid oxygen as 1.141 kilograms per liter, we have an initial mass of around 570 kilograms of liquid oxygen. As a person needs around 0.85 kilograms of oxygen per day, the 6 astronauts have enough oxygen for over 100 days. As for the water, we said we will bring 370 kilograms as stated at page 22, table 5, cargo weight distribution. We did calculate that number by estimating the human need of water per day to be between 2.5 and 3 liters, bringing water for a week for the 6 humans and bringing water for 2 aeroponics towers. In the worst case scenario, the entirety of the 370 kilograms of water will only be used by humans, keeping them hydrated for over 3 weeks. If needed, the crew can direct the complete focus to setting up the water extraction systems, getting to the ice deposits thanks to our rovers. The water can be used as a source of oxygen, but since we haven't hit the 30-ton limit, even more water can be brought from Earth. You also mentioned that we cannot afford cut corners when it comes to crew safety. We are talking about human lives here. We definitely kept that in mind when we have been developing our life support systems. You also extracted that AstroMineX plan was to extract and store 9,000 liters of water within the first 12 days. This is ambitious and almost meets their total requirement. However, there is a catch. The stated storage capacity is only 4,000 liters, which is less than half of what they would need. Where would you store it? While all of this is completely true, we have to remind you that, as stated at page 22, table 5, cargo weight distribution, we will bring around 40 aeroponic towers, each with a capacity of 175 liters, calculated at page 12, operational details. This brings us to a total of 7,000 liters capacity just within our aeroponic farm. Added with the 4,000 liters mentioned before, we actually have an 11,000 liters water capacity, well over the 9,000 liter mark that we have set.
Now we will address the location issues. Let's clarify a few key points. First, regarding the rarity of small craters on Mars, it's important to note that while the large craters are more frequently studied due to their prominence, small craters of about 15 to 30 meters in radius are not extremely rare. According to studies in Martian surface imagery, there are numerous smaller craters that have been identified and cataloged by missions like Mars Reconnaissance Orbiter. These craters are well documented, and our proposed landing site at 6.08 degrees north and 155.72 degrees east in Elysium Planitia includes several small craters that meet our requirements for natural protection against dust storms and radiations. Large craters, such as those over 2 kilometers in diameter, do not provide the same level of containment and protection necessary for the initial setup of our mission's inflatable habitats. As for your concerns regarding the use of lava tubes, we acknowledge that the challenges, but emphasize that identifying suitable lava tubes through satellite imagery is well within our current technological capabilities. High-resolution imagery from orbiters such as Mars Odyssey and the Mars Reconnaissance Orbiter allows us to locate and assess the structural integrity of these tubes with considerable accuracy. Moreover, utilizing lava tubes is a strategic choice that leverages natural formations to provide stable, shielded environments essential for long-term habitation. While the construction methods for outfitting these tubes with life support systems are indeed complex, they are based on tested engineering principles and the growing body of research in situ resource utilization and habitat construction in extraterrestrial environments. You mentioned that our power systems, such as wind turbines, bioreactors, and solar panels, would be toast in a dust storm. As mentioned on page 6, energy generation, the solar panels are not just solar panels, and not just the solar panels will use electrodynamic dust shield. The studies are mentioned on page 24, bibliography. As for the wind turbines and the methane engine, I think that's what you meant when you said bioreactors. They are secondary sources of power. I'm sure it would be it would actually benefit us to have dust storms after the wind turbines are assembled. If your concern, which you have not clearly stated, is about the dust affecting the electrical components of the wind turbines, we will use carbon fiber dust filters.
Now, regarding the weight limitations concern, you I want to ask, how have you calculated that to bring additional habitats and construction equipment for the lava tubes settlement would exceed the mission's weight limitation? When we stated at page 11 underground habitat that the total weight of these components is estimated to be around 2 tons. As for exceeding the mission's weight limitations, as you can see, we calculated at page 22, table 5 cargo weight distribution, that the total weight is estimated at around 25 metric tons. So there is still quite a lot until we hit the 30-ton mark. Still, at page 22, table 5 cargo weight distribution, after a careful analysis, it is safe to state that no component can be deemed as not essential to our mission. Now regarding the asteroid mining concern. First of all, we have estimated each of the 2 drones with fuel at 1.5 tons, not at 3 tons as you mentioned. We also never stated what kind of fuel we would use for the ionic thruster. You have considered we would mine asteroids such as the 4947 in Kasi, which you state is quite small, 520 meters in diameter. We have a source which states that it is approximately 831 meters in diameter, but that's irrelevant. Here is a soccer field. It is around 100 meters in length. So the asteroid suggested would be a little over 5 fields in length. I don't really know by what standards is this asteroid small, but we intend to actually mine small asteroids. Our plan focuses on extracting resources from smaller asteroids, while larger asteroids will only be marked for future missions, ensuring minimal risk and maximum efficiency. This initial mission serves as a vanguard for later, more comprehensive mission. We also never mentioned mining such large asteroids. With a limitation of 30 tons and 6 members of the crew, you cannot mine the whole asteroid belt with ease. Now you mentioned that our fuel would actually be around 13 million tons. Let's do the math. So we know the radius of Mars as 3,390 kilometers. We have chosen the height at which our drone will start its mission at 310 kilometers in the low Martian orbit. We know the gravitational acceleration of Mars. We know the universal gravitational constant. We know the distance between Mars and the asteroid belt. Our final speed of the drone is 10 kilometers per second. This is what we want. We know the mass of the drone, as I stated, 1.5 tons. We know the engine efficiency at around 70%. And I have calculated the calorific power of burning a kilogram of our fuel. This is actually very simple. Hydrogen burns with oxygen in a simple reaction, as you can see. So we will choose a ratio between the hydrogen and the oxygen as 2 to 1. The enthalpy of combustion for hydrogen is approximately 286 kilojoules per mole. This means that for each mole of hydrogen burned, 286 kilojoules of energy is released, giving a 2.2 to 1 Meson ratio of hydrogen to oxygen. For every kilogram of fuel there is 0.6 kilograms or 666 grams of hydrogen, meaning 333 moles of hydrogen, since we know the molar mass of hydrogen to be 2 grams per mole. Therefore, the energy gain from burning 1 kilogram of fuel is around 95.33 times 10 to the power of 6 joules. Now we don't know everything. We don't know the initial speed of the drone. We actually know the mass of Mars, but we didn't need that. Now we want to find out the time of travel from Mars to the asteroid belt, and we need to know the mass of the fuel. So I can show you the calculus. It's actually not that hard, and we can see that a trip to the asteroid belt from Mars would take 86 days, 19 hours, and 20 minutes. Now I have calculated that for the drone, which weighs around 1.5 tons, you would actually need 995 kilograms of fuel, which makes the 30 million tons of fuel affirmation just completely false. We have also not forgot about the comparison that you've made at the rovers. It was actually not funny, and it was also inappropriate. And it was also incorrect. A North Atlantic right whale has actually a testicle of around 9,000 kilograms, 900 kilograms, which is around the fuel mass. So please, at least when you make such comparisons, you get the right data. Now, one of the misunderstandings when you have calculated is that maybe you have not seen that our cargo will be in the low Martian orbit. So we will not have any problems with escape velocity. Now the rovers. Firstly, comparing two similarly looking things does not mean they should have the same properties. As we all know, what matters is on the inside, not on the outside. The lunar buggy is made of aluminum, titanium, and steel. Titanium has a density of around 4,500 kilograms per meter cube. Steel has a density of around 8,000 kilograms per meter squared. Cube, sorry, while aluminum has a density of around 2,700 kilograms per meter cube. Carbon fiber has a density of 1,600 kilograms per meter cube, which is way less than way less than we have all the materials mentioned before. We have estimated our rover, our Discovery rover, to be 200 to 400 kilograms, while we estimated it at 20 kilograms. Here is how we calculated that. So we know the density of both carbon fiber and aluminum. We know the tube radius, the inner radius of the tubes at 3.5 centimeters. The outer radius has 4 centimeters. The length of a tube at 3.5 meters. The other length of the tube at 1.5 meters. We know the floor thickness as 1 millimeter, 0.1 millimeter, and the floor length and width. So we have calculated first the surface and then the volume. The mass of the aluminum is actually 7.9 kilograms. The mass of the floor, which is made from carbon fiber, is 8.4 kilograms. Add that to around 60 kilograms. With the 2 kilograms of wheels, the total will be 80 kilograms. There may also have been a misunderstanding here, because when we stated the weight, we only meant the frame, the wheels, and that's it. We didn't mention the batteries, which are actually stated somewhere else. Now my colleague Edward will tell you about the communication system.
Yes, we received critics about our CubeSat system. So as I mentioned in the last meeting, I won the European Space Agency's Romanian CanSat competition. Well, why is that important? Well, not only have I done my research and gained theoretical knowledge, but I also have this experience in my repertory, which gives me practical knowledge. At the competition, the committee asked us why we should use this device instead of a performance drone. The answer is because it is much cheaper and has a better life expectancy if you add solar panels. Our device costs less than $200, while a performance drone starts from $1,000. When you move that scale in space, the difference would be even bigger. So you specified that the lightest CubeSat was 750 kilograms, but the CubeSat isn't a commercial or a military satellite, which needs to provide extra services to the people. So CubeSat is a device which can be built only to collect data, transmit data, or lead a connection to other devices. Each cube weighing only around 500 grams will result in the cube itself being small. We will use one U CubeSat satellites, meaning they are 10 centimeters by 10 centimeters by 10 centimeters. You mentioned that the stated weight of half a kilogram really isn't applicable. A mini laboratory in a mini satellite is looking for answers. Therefore, will be no problems with deploying each device in Mars atmosphere. We would rather have over 700 devices, and in a worst case scenario of a big asteroid coming towards Mars, it cannot hit the entire surface of the CubeSat network. That means at least some of the CubeSats will survive, which is enough to establish a connection with Earth, rather than relying on a singular, just geostationary satellite, which in this case, once destroyed, it's over. The communications will be no more established, and the life of the people on Mars will be in somewhat danger. Our CubeSat network.
AstroMineX, you have 5 minutes to complete your defense.
Okay. Well, our CubeSat network will be located at around 300 kilometers in the low Martian orbit. So using this information, I have calculated also the frequency. Now my colleague Matei will continue the
presentation is actually over. I want to mention before we end that it has been an honor and a privilege to have participated in this contest. And obviously, I will have to thank our student mentor, which is actually here today, Shreya Savant. She actually helped us a lot when developing our project. And I hope we have clarified all of your concerns. If not, we can still answer questions. And thank you for your time and your attention.
You all have done a wonderful and thorough job. I'm so proud of you as a team and so happy that you've had such a wonderful mentor. If anyone has questions, we have 3 minutes remaining for their time for questions. Just put them in the chat or unmute yourself and ask. Remember, we're speaking kindly to each other and no personal attacks. If there are no questions for clarification, we will take a 2-minute stretch break and we will return with Team Aspera.
So I'll stop my share.
Pardon?
Or any questions?
Okay. 2-minute break and we will be back with Team Aspera.
Okay.
Okay, we are back and we are ready for Team Aspera to present their defense. You may share your screen. If you're talking, you're muted.
Okay, hello everyone. We'd like to firstly thank Team AstroMineX for the defense on their defense presentation. Team Aspera is thrilled to be here at the third and final round, the rebuttal, and ready to defend the claims that were made by AstroMineX in round 2. Team Aspera's Mars mission concept represents a meticulously balanced and scientifically grounded approach to establishing a suitable human presence on the red planet. Unlike other teams, Team Aspera's approach doesn't rely on speculative technologies or overly ambitious goals. Instead, we've designed a mission that balances innovation with practicality, ensuring the highest probability of success for this critical step in human space exploration. Our design addresses the core challenges of Mars exploration while laying a solid foundation for future missions and potential colonization. Next slide, please. Many of AstroMineX's claims are based on hypothetical scenarios or what-ifs. What if the rover breaks down? What if the crew dies of cancer due to radioactive exposure? They are leap-offs and apply to any mission design, including our own. Next slide, please. And for the table of contents, we'll follow the same format that we always do, human ops to engineering to science. Next slide, please. I'll start off with human ops and crew selection. Next slide, please. We were unsure whether Team AstroMineX were questioning the role of the medical officer or the sole medic when not around during an emergency, so we decided to answer both. First, the inclusion of a medical doctor/psychologist in the Aspera mission is not only necessary for addressing medical emergencies and maintaining crew health, but also for providing psychological support and contributing to various mission-critical tasks. Their multifaceted role enhances the overall mission efficiency and safety, ensuring the success of the 15-month Mars mission. The main role of the physician/doctor is not just about providing aid in medical emergencies. Given the isolation and communication delays with Earth, immediate medical intervention is crucial. A medical doctor can address a wide range of health issues from minor injuries to severe conditions like appendicitis or dental emergencies. However, they are not going to be twiddling their thumbs or waiting for disasters to happen. The rest of the time, they will monitor health, provide psychological support, and will conduct human physiology scientific studies, such as studying bone density loss and contributing valuable data for future missions and enhancing our understanding of how the body adapts to Mars. In collaboration with the astrobiologist/botanist, the medical officer can assist in experiments related to growing plants in the Martian soil due to their transferable skills. Lastly, the medic can be cross-trained in basic engineering and maintenance tasks, providing additional support to the engineering team, ensuring redundancy in critical skills. Next slide, please. AstroMineX also provided a hypothetical scenario in which the medic is on the Beagle and there is an emergency at the habitat. Since an incident like this may occur, the medical officer will cross-train other crew members on a regular basis in medical procedures and emergency response, ensuring that all members of the crew are prepared to handle medical situations if the physician were to be incapacitated. Next slide, please. The allocation of 500 kilograms for the comprehensive medical kit, telemedicine capabilities, and health monitoring system is justified based on the critical need to ensure the health, safety, and crew of the 15-month Mars mission. The detailed breakdown demonstrates that each component are given in the next couple of slides. Next slide, please. Our ethos is human-centric, and this is reflected in the breakdown. The medical kits are designed to address a wide range of health scenarios, from minor ailments to serious medical emergencies. Telemedicine is crucial for consulting with a specialist, providing additional medical support and ensuring that the crew receives expert advice for complex medical issues. Next slide, please. Exercise equipment is essential for mitigating the effects of microgravity, such as bone density loss and muscle atrophy. The inclusion of a treadmill, resistance exercise device, and cycle ergometer ensures that the crew can maintain their physical health. Health monitoring devices provide continuous data on the crew's health, allowing for early detection and intervention of potential health issues. Thank you very much for listening, and I'll hand it over to Nidhi, who will continue human operations.
Hi. So in terms of choosing a mission commander and the selection criteria, as well as their being chosen based off of their profession, we do believe that it is possible to choose crew members as well as the commanders based on their profession. And I just wanted to mention that our report also does include selection criteria for the commander, including that they will also need an engineering skill set. And this just helps to boost our engineering team and make that a stronger aspect. They also must have prior spaceflight experience, be an astronaut, as well as well-versed in mechanical and electrical systems of the mission, as they will be making sure that all systems are operating and in charge of the team that will be leading those. Next slide, please. So in terms of the suitability, of the commander role, we are also basing this off of historical precedent. There are multiple commanders previously seen with engineering backgrounds, which has made it invaluable to handling unexpected situations. This includes examples such as Reed Wiseman, Kelly Hadson, and Peggy Whitson. Next slide. And there's also rotating leadership, as in commanders with backgrounds in medicine, psychology, or geology can provide knowledge within each other and creates an interdisciplinary approach to ensure that we have a well-rounded team that can attack any challenges that they face. Next slide. And in terms of the personal items that they will be bringing, this was a typo. So it's actually 30, not 300. So each one is 5 kilograms per person. And these personal items are essential to the crew, as it not only benefits them with being able to carry like hygiene as well as clothing, but also it benefits them in like a mental health perspective, as they're able to connect back with their lives on Earth. And this includes essential personal items like mementos, photos, as well as they're able to bring like an electronic device such as a tablet. Next slide. And in terms of our plan for food, we do want to prioritize crew health and safety. And the main priority in doing that is being able to ensure that there's enough food. We do not want to take risks, especially when lives are involved. So we would rather put ourselves in the scenario where we have too much food rather than not bringing enough, as well as the amount of food that we bring is our backup, as it's dehydrated food and will be able to help us in any case, an emergency. Next slide. Also, we want to focus on reliability and redundancy. Unlike the International Space Station, which receives regular supplies, we will be too far away and will not be able to have access to resupplies. This will make sure, so in that case, we cannot rely on more food being able to come in an emergency, so we need to bring it all with us. This is also a redundancy plan, which would be in place until they can grow food from both the hydro and aeroponics, as mentioned in page 19 of our presentation. And each crew member does require around 3 to 3.5 liters of water per day, but that food can also be used for food preparation, food rehydration, drinking, as well as hygiene purposes. And this initial supply is their lifeline and is critically important to the mission. And then the next question was, if you bring so much food from Earth and water, have we taken account the weight for water tanks, refrigerators, and power supply? We have taken account for those, and we likely have a total power budget in the range of tens of kilowatts. And for example, we will assume a conservative 20 continuous power supply. And the weight for the containers hasn't taken into account. We have extra weight in our calculations that allows for this included in our paper. Next slide. And then there was the critique that by 2030, their mission will be the AstroMineX's mission will be over and ours will just be beginning. Our choice in timing is that a later mission start ensures that all technologies that we have decided to use will be ready for usage and have gone through the necessary steps to ensure success once on Mars. This includes various testing of our habitat, rovers, and spacesuits, as well as we need to train the crew and select the crew to ensure maximum success and test all systems on Earth so we don't find design faults while on Mars, as that will make it a lot more difficult. It also takes time to prototype rovers and habitats and make sure it goes through necessary testing and that to make sure that they are feasible. We also have that approximately planned missions will take place between 10 to 30 years after the time that they are drafted. And so we are already cutting it shorter on the lower than 10 years side, but we think that that should be enough time as we want to make sure that everything will be working and everything will be feasible. Next slide. And I'll hand it off to Leo for engineering now.
So just quick note before we start. It's the southern blue whale, which has a whale testicle mass of 900 kilograms. The blue whale is a mass of 50 kilograms.
Northern, from the north.
So the AstroMineX team said, you said you would bring 2 kilopower modules weighing around 1,500 kilograms each. Oh, sorry, 1,500 kilograms. The smallest Gen 4 nuclear reactor that I found is 200 tons. So our report stated that the reactors weighed 1,500 kilograms each, not in total, so that would be 3,000 kilograms in total. The reactors have already been tested at the Lawrence Livermore National Laboratory. They're planned to fly on NASA's Artemis program. If you'd like to see the source for the mass, consult source number 28 on our report. There is a 2016 NASA presentation which listed the mass of these reactors as 1,800 kilograms, but Aspera decided to go to the latest source. And that source is listed down below. And either way, the Aspera mission has more than enough spare mass to use either design. So keep in mind that this is a very light reactor because it's meant to be flown in space. Next slide, please. So yeah, you can see different masses here on a study by on a presentation by NASA's Glenn Research Center, Interagency Advanced Power System, and Johnson Space Center Group. And you see the 10 kilowatt highly enriched uranium Mars reactors weighing 1,484 kilograms. Next slide, please. AstroMineX also said, have you taken into account any sort of protection for the astronauts? Because if not, they will get cancer and die before they even get to Mars. I'm assuming that you say die on Mars because the reactors aren't flying with the astronauts on their way to Mars. And even if you bring protection, this will require volume and mass, and there is no 100% protection. What are all the cooling systems for the reactors? How will the heat dissipate, seeing as the atmosphere of Mars is very thin? Next slide, please. And so we'll start with a radiation problem. This radiation problem, especially with the kilopower nuclear reactor, has been studied very extensively. The kilopower, and all of this is included in the mass of the reactor. The kilopower would use lithium hydride for neutron shielding, and either tungsten or depleted uranium for gamma shielding, as it offers a significant mass advantage to lead. You can see right there on the figure in the middle, or on the right, the lithium hydride shielding layer. You can also see a graph of the shield mass versus separation distance for a 4 kilowatt kilopower reactor. Now our reactor will be 10 kilowatts, but this gives a nice idea of a scale. And their scale maxes out at 25 meters. And so we could easily land our reactor hundreds of meters away, making the risk of radiation near zero. And all of this radiation shielding equipment is included in the mass estimate. And keep in mind that our base and shield are already radiation shielded to protect against the radiation in space. And so it's safe to say that it's almost perfect shielding. Next slide, please. And so now onto the cooling. So you can see all that figure of kilopower right there. It's got a really, really large circular dish, and that's used to evaporatively cool the reactor. So for instance, if you have got a cooling system failure, that thing will keep the reactor from having a meltdown. In tests at Lawrence Livermore National Laboratory, the reactor showed no significant changes on internal heating over a 24-hour period when coolant failure was experienced. That's not to say that coolant failure could keep with a coolant failure, eventually the reactor would overheat, but over a 24-hour period, it'd be just fine. As a primary source of cooling, kilopower uses sodium heat pipes, and that's also evaporative cooling. To transfer the energy from the reactor to the Stirling engines, the two figures on the bottom right there, and the one on the left, you can see are the Stirling heat pipes, which cool the reactor and transfer its energy. Next slide, please. And so AstroMineX said, what if the reactor breaks down? Then you don't have any other type of power supply. So the first point is we do have any other type of power supply, and that power supply is located within the rover. The Beagle uses 3, not 2, not 1, but 3, which would be more than enough to power the base. Ballard FC-Move XD 120 kilowatt PEM fuel cells, and these could easily be used to power the base for low durations. Obviously, you couldn't power this for the entire mission, but you could easily power it for a week or a few days, if in time for the astronauts to go and potentially try and resolve any problems with the main power source. And they're extremely reliable as they have no moving parts. The mission also includes plans for water extraction from the Martian ice, and this can be electrolyzed to produce hydrogen, which can be used to power the Beagle's fuel cells. It's also worth to note that nuclear reactors don't really just break. If you take a look at the nuclear reactors on board nuclear submarines, there's never been a meltdown in the entire history of nuclear submarine nuclear reactors, and so that tells you something about their reliability. Next slide, please. So AstroMine said, you mentioned that you only have one rover. This rover, which we estimate is 7.5 tons, which is about a quarter of the allotted 30 tons. That's a lot for one rover. What happens if it breaks down and impacts when you land on Mars? You don't have a rover anymore to explore as you wish. So the ability to repurpose the Beagle's fuel cells and focus on habitat-based research and leverage in-situ research capabilities will allow the mission to continue, albeit with adjusted timelines and priorities. So you'd obviously do less science, but you'd still get a lot done. The crew's diverse skill set, including the mission commander, who's an engineer, will allow them to adapt and probably fix the rover, continuing to pursue key objectives despite this setback. And in previous missions, there was only one rover, so the precedent exists of landing only one rover. Previous missions, we say Perseverance, Curiosity, etc. We'd also like to note that we're not responsible for landing the rover in this competition, and so I think we can just assume a successful landing of everything on Mars. Next slide, please. So AstroMine said, you mentioned that theta is 50 degrees, correct? What if the crater is steeper than this and you cannot get out of the rover out of the crater? It's unusable since you can't move it, since it's 7.5 tons. So the first point is we've got a topographical map of the surrounding region around the landing site. You can see the crater. It's a bit of a dual crater at the figure on the right there. And it's not steeper than 50 degrees. You can go on this website called Mars Trek, which will give you very, very good topographical and very accurate topographical information, which you can use to calculate the slope. Yeah, with enough power, and we're going to talk about how much power the rover has soon, the mass of the rover should not stop it from being able to go out of the crater. And also just choose a route which doesn't put it across a 50-degree slope. Just go around the hill is generally the idea. Next slide, please. And so we wanted to clear up a little misunderstanding. A large rover doesn't mean it's underpowered. The rover will have an average power draw of 110 kilowatts, which was calculated in the image down below. Each motor produces 210 kilowatts of power. And so I think you can already see that it's more than enough. One motor would be more than enough for the entire rover, but we've got 4 of these motors. And if the load is distributed across all 4 motors, each motor will be running on only 8% power. Now this is fairly normal, especially for this type of high power electric motor, but the point is, if the Beagle needs power, it can get a hell of a lot of power. Next slide, please. AstroMineX also said that you've estimated the EVA6 to be at least 1.5 tons. That means its suit is around 250 kilograms. That's correct. So I really don't know how you can't do tasks with a suit so heavy, even with the lighter gravity of Mars. So we said 150 kilograms for one suit, 900 total. That was a typographical error. You might know that we had to do the human operations part in a little bit of a rush. Furthermore, 150 kilograms for one suit is very normal as far as spacesuits go. Next slide, please. AstroMineX also said, which is the domain of frequency that the satellites, the rovers, the settlements, the suits are going to communicate with the planet Earth? And also, I have to ask, how will the communication systems work over long distance? So we plan to communicate directly with the NASA Deep Space Network by primarily utilizing the Martian Reconnaissance Orbiter in Martian orbit. But if you're curious about the exact bands we're using S bands, so that's 2 to 4 gigahertz for telemetry, tracking, command, operations. X band, that's 8 to 12 gigahertz, commonly used for deep space operations due to its ability to carry more data. And K band, 27 to 40 gigahertz, offers higher data rates and is used for advanced communication needs. So if you're not communicating too far, you'd use 27 to 40 gigahertz, for instance, for real-time communication with suits of the rover. Next slide, please. So AstroMineX asked, how will you split the cargo if you come with all the cargo? We're going to have 2 launches. If we fail to say this in the report, we apologize. That was a mistake. The first rover will have the rover, the nuclear reactors, the ice drill, an electrolyzer, and a portion of the food supplies. That's to generate some fuel before we for the rovers before the astronauts land. Second launch 2 years later, everything else. Next slide. Yeah, that's about it for me. I'll pass it off to NA and Tene.
Thank you, Leo, for those things. So now I'll be talking about the critiques that AstroMineX said about our science. So first they said that we have a drill system of 40 kilograms, and we said that the craters contain ice deposits as deep as 40 meters. So how could you drill with a system of only 40 kilograms as deep as 450 meters? So in regards to this, we appreciate Team AstroMineX's dedication to ensuring the accuracy of facts and figures. However, we would like to clarify that at no point did we state that the red water drill would reach a depth of 450 meters. Our intention was to highlight that the ice deposits themselves can extend up to such depths. The ice deposits within the crater range from just a few centimeters beneath the surface to several hundred meters deep. This means that even a drill capable of reaching just 1 meter could access these valuable ice deposits. Our drill, like most other base systems, will be powered by electricity, and to ensure efficiency and durability, we will utilize advanced lightweight materials such as carbon fiber composites and titanium alloys for the drill structure. Additionally, we will implement a modular design with segmented drill rods that can be added incrementally as the drill progresses deeper. This approach not only maximizes the drill's effectiveness, but also ensures that we can adapt to varying depths and conditions within the crater. By leveraging these innovative materials and designs, we aim to achieve our mission objectives with precision and reliability. Another thing they said was that we need to take into account air composition, and they said we need 0.84 kilograms of oxygen per day for 6 people for 300 days, and a total of 1.5 tons of oxygen will be brought from Earth. And they asked if we have considered the weight of the tank and things like that, and if oxygen will be liquid. So the oxygen will be in a liquid state, and to calculate the weight of the tanks, I've done some calculations. So 1.5 tons was 1,500 kilograms, which you can calculate the volume would be 1.3 thousand liters. Now, we know what we did was we used the amount of H cylinders, which are typical kind of things to store oxygen. And we realized that you would need 0.19 H liters because one capacity of 1 H liter is 7,079 liters of oxygen. And that means 1 H liter is only 60 kilograms. However, now to process that liquid oxygen back into gaseous oxygen to breathe, we would need different tools. Like we would need a cryogenic storage tank, vaporizers, a pressure control manifold, and piping and valves. So the cryogenic storage is estimated at around 3,250 kilograms. The vaporizers would be 500 kilograms. The pressure and control manifold would be 100 kilograms, and the piping and valves would be 140 kilograms. If you add all of this up, you get 3,090 kilograms. And this puts us just under our mass limits, and I have a full mass breakdown of our whole mission in the upcoming slides. Also, technology will be better by 2030, so this weight will be reduced, so we will be safely under our mass limits. So as you can see, we have successfully addressed this critique. Another thing they said was that the communication systems could fail, and if we have a backup plan. So for a backup plan, Creating a backup plan for a Mars mission involves addressing unique challenges. And to address these challenges, we have kind of 4 different things in place. We have our redundant communication system. We'll utilize multiple communication methods, including direct-to-Earth links, and also we will relay with different satellites orbiting Mars. This ensures that if one system fails, another can take over. Next, we have our relay satellites. As I said before, we'll use orbiters around Mars to relay data between the surface and Earth. This method is more reliable and redundant, and then direct communication due to the power and mass constraints on our rovers and our HAT.
Team Aspera, you have 5 minutes to complete your defense.
We will also be using high gain and low gain antennas, as I said before, as Leo stated before, with the Ka band frequencies and the X band frequencies. And we'll also conduct regular testing and drills on what to do if our communication systems fail. By implementing these strategies, our mission can maintain our robust communication capabilities. In terms of mass for these extra communication tools, we can assume a range of 750 to 1,500 kilograms. So if we assume the maximum, this still gives us a total mass breakdown of 28,617 kilograms for a whole mission. So this still gives us room for error, and technology will improve, so mass will go down. Another thing, AstroMineX said that why would we use a hydroponic garden instead of an aeroponic garden, which obviously uses up a lot less space? They are correct in noting that an aeroponic garden requires significantly less water, and this is precisely why our laboratory has one. We are also fully prepared for the possibility of our H2O processor breaking down and needing repairs. Given that aeroponic plants can perish within 1 to 3 hours if not exposed to water, we have also established a hydroponic garden as a backup. This dual system approach ensures that we can maintain our plant growth and research activities without interruption, even in the event of equipment failure. By having both aeroponic and hydroponic gardens, this increases redundancy, and we can leverage the benefits of each system while mitigating potential risks. At this moment, we'd like to take a moment to recognize the members of our team. Myself, Tanae, Leo, Nidhi, and Ane. We'd also like to extend our thank yous to Peyton Hemmond, which she was our mentor for this competition, and she was a very valuable source of support and helped us a lot with any questions we had. We'd also like to thank Miss Willett for being our point of contact throughout this competition, and the Mars Society for hosting this competition.
And I'd also really quickly like to thank all the other teams. You guys did a really great job, and this competition wouldn't have been any fun without you guys.
And thank you. With that, the defense rests.
Thank you. Absolutely wonderful defense of your team. I love your logo. Love all the hard work you guys did preparing all the data, etc. Thank you so much. Next, we have Team Tomas Mars. I hope am I saying that right?
Yes.
Okay,
Yes,
thank you.
thank you.
Don't we
And
have some time to ask some questions and a stretch break?
we have 2 minutes before the end of the time, and then we'll take a stretch break. Do you have a question, Team AstroMineX?
Just a small one.
Okay.
So I'm a little confused. The defending was quite an extension of the project, and we still haven't gotten clear response about fundamentals such as the protection from radiation. What exactly does it consist of?
Hi, I can answer that right now if you'd like.
Okay, go
Yes.
for it.
Is there any possibility that we can bring the slides back?
Yes.
I think Tanae, you're on the slides, right?
Yeah, let me just bring them up.
Thanks a ton. 1 second, we're just bringing the slides back.
Uh,
1 second, sorry.
Okay, there.
All right. Could we go to the radiation slide real quick? I think it's slide 20 something. There. After, next. There, exactly. Yeah. So I'd like to preface by saying all radiation measures are included within the mass of the kilopower. There are two types of radiation produced by nuclear reactors. There's neutron radiation and there's gamma radiation. Both are pretty deadly. If I'm not wrong, I think that neutron radiation is a little more deadly. And without this radiation shielding, and if the astronauts were right next to the nuclear reactor, it'd be pretty deadly. But luckily, there is radiation shielding. To shield it against neutron radiation, there's a layer of lithium hydride surrounding the nuclear reactor, which can absorb neutrons. And there's also a layer of tungsten or depleted uranium. We don't know which. Which one is exactly better and offers the best radiation protection to mass ratio is not yet known. Either one would be completely fine, but the difference would be marginal. So you would either use tungsten or depleted uranium to gamma shield. All of this is included within the mass estimates of the reactor. Right there, another measure that you could take is by pushing the reactors out further than the base. You can see on the graph right now the amount of radiation shielding needed compared to the separation distance, so that'd be base to nuclear reactor needed to make it safe. This is for a 4 kilowatt reactor. Ours are 10 kilowatts, so you can imagine that they have to be further away. This graph is just to illustrate that distance acts exponentially on the amount of radiation received. And so, for instance, you can imagine that if we put the reactors hundreds of meters away from the base, the risk of radiation combined with the lithium hydride and the depleted uranium or tungsten shielding would make the risk of radiation near zero. Something else to consider is that both our base and the suits are equipped with shielding against radiation. This is to shield against cosmic radiation, but it also has the exact same effect when shielding against radiation from nuclear reactors. We don't need it for nuclear reactors, but it's just something to keep in mind to further reinforce how much shielding we have against this. I hope that makes a little bit more sense why the radiation problem really isn't a problem whatsoever, and it's been discussed extensively.
Thank you, but you have also mentioned that you could place the reactor extremely far away from the settlement. So,
hundreds of meters, yes.
How much did you say?
Probably 50 to 60 meters would be more than enough. But really, you could place it as far away you can. Power lines really aren't very heavy. Of course, we haven't included those in the mass estimate, but seeing as we have over a ton to spare in the mass estimate, I'm sure we could fit those in.
Okay, but have you still taken into account a backup for the rover? Do you have any other way of moving?
Pardon?
In case the rover breaks.
In case the rover breaks?
Yeah, the worst.
If the rover... I don't quite see how the rover breaking has anything to do with radiation. I'm sorry.
Leo, I can take
Not
this
with
one.
radiation.
I can take this question.
Go ahead.
So in terms of the rover affecting our scientific objectives, we also do have a variety of scientific experiments and studies being conducted at the habitat, which is, as we said, in the situation that the rover does break, we can have our team, because they are flexible and can be split up into sub-teams. We could have one sub-team focus on current habitat based, located on the habitat that requires no moving. And the other sub-team could focus on fixing the rover to get us moving again. But moving with the help of the rover does not contain all of our sole scientific objectives.
I know that. And you have also mentioned that you are not responsible for the landing, but you still have to take that into account. So I still have to ask if the worst case scenario and it just breaks beyond any kind of reparation possible, what then?
Then the astronauts really just won't be driving anywhere.
Okay,
Yeah,
so
then at that point they can just continue their scientific objectives
can hike.
that occur on base.
It's extra cardio, right?
okay, but it's kind of a hard type of cardio with
Listen,
sorry.
listen.
One last question.
I understand. But we are running out of time because we have another team that has to present and
No.
pick and
The
pick.
last question.
And you need to wait until the very end, okay? Because we
No.
have to let
Sorry, I
the
wanted to say it's fine. Our
I
presentation a bit shorter anyways.
uh-oh.
I had also a
It's
question
fine.
for them,
just
but
30
Okay.
seconds. 30 seconds.
We're out of time for that. You have to wait till the end. I have to allow the other team to take their turn for the same time. You can also put in the chat your questions and discuss your questions in the chat with each other. Please do it publicly so I can view it. Please do not attack each other personally. And realize these are not perfect plans for any team. Even real astronauts who are going to be going to Mars, there are going to be things that go wrong. There are going to be things that don't have an answer. So please keep that in mind, and be kind and do not attack people personally in the chat or on here. So we need Team Tomas Mars. Let's take a 1-minute break since we ran over. Team Tomas Mars, you will be up in 1 minute. Everything else, please put in the chat until the end of the presentation. Thank you.
We'd be more than happy to answer any questions out loud at the end of the presentation. Thank you.
You can take your slides down. Okay, Team Tomas Mars, are you ready? When you are ready, you may share your screen and start the defense portion of your project. You have the floor.
So we wanted to say that first of all, due to our relatively limited attendance, we don't know if we'll be able to answer all of the proposed questions. Despite this, we'll do our best to answer as many of them. And also because we won't be sure if we'll answer all of them, we don't have a proper visual presentation because it'll be pretty short and we didn't want to just screen share 2 or 3 slides. Now, I wanted to start off by saying that we all appreciated all of the critiques. It helped us, keep our facts in check. And also, it was more fun. It's more fun when you have to think about all of this. Now, for the first critiques I would like to address were the ones from Tomas Mars regarding the solar panels and the fuel cells made out of the percolates. And after doing some more research on it, I can say that you are very right. I try to find something and I can't make a proper rebuttal to those. Onto the ones I can make a rebuttal for were still from Tomas Mars regarding the critique about us not, because we do not have a proper scientific research in our mission purpose, the crew will get bored. This is, well, kind of also relatively subjective because this is up to the crew, and people can be trained to not distract and possibly not bored and such, and we don't know if it'll be an issue. Plus, we believe that as a mission purpose, the best we can do for this 1.5 years is not a lot of research or such. It is, first of all, to test how well we can do and set up for future missions. We can basically test how well we can survive in this environment, and also see what materials we can use and how to best use them in this time. So our purpose is a bit lackluster because we believe that it's best to save this research for a later mission when we will have more personnel and more equipment that we can use. Besides that, I don't have a lot else to say, really. If my colleague Andrea has anything else to say, I'll let her do so.
Right. So about the fact that our amount of food was critiqued, I think another team mentioned that we have too much food and that it might be too much to transport. I want to mention that aeroponics doesn't really take up that much space, and besides, we will not be taking the plants directly. Obviously, we will be taking the seeds first to be transported from Earth, and maybe obviously the soil for the soil farms, because we have both aeroponics and soil farms. And this is about it. Actually, as it has already been mentioned, more food is always better than less food. Like having excessive food is always a better option, even as a backup, even as in any situation. And sadly, because we are not too many people, this is about everything I can answer.
Now, to finish it off, I want to say that we, as a team, we are all very thankful for being able to participate in this contest. We thank Miss Nicole for, despite our past mishaps, allowing us to keep on participating, and thankful to the rest of the teams for asking the questions and making it more fun for everybody.
Is that the completion of your defense?
Sadly, yes.
Sadly, yes. We
Thank
don't
you
have much
very
more.
Thank you very much. Sometimes when we work as a team, the biggest lesson is not everybody knows what teamwork is, right? So it's not your fault if your team didn't pull their weight. I appreciate you guys being here and doing the best you can. This is a very complicated contest because no one's ever actually gone to Mars before, right? So we are sharing ideas, and in your own way, you are helping move humanity to be a multiplanetary species, and that's the whole point. We're learning many things and moving humanity forward. So I appreciate all of you being here. And I think there are a couple of questions from the previous team. Leo and Team Aspera, if you would like to answer Matei's question.
So I'd like to answer the question about what if the rover breaks down and can't be fixed, and the 150 kilogram suits are pretty heavy. So the first point is 150 kilograms in Martian gravity weighs around 57 kilograms, and that really isn't very unrealistic. Obviously, you won't be going as far, hundreds of kilometers as the rover, but you will be walking around the crater. Second point is you've got to take risks. If you look at the Apollo program, the ascent engine, there was only one ascent engine to get back from the moon. If that failed irreparably, the astronauts on the moon would be dead. But that was a risk that was worth taking in order to advance human knowledge. The decision to make one large rover with a large capability instead of splitting it into two smaller rovers with smaller capabilities was made in the same spirit. So if it breaks irreparably, then yes, the astronauts can't drive anymore. But the risk of it breaking is extremely low. We've got lots of redundancy. We actually only need 2 fuel cell units, but we have 3 in the for the sake of redundancy. So in the unlikely event, very unlikely event, that it breaks down irreparably, well, it just does. There's nothing really you can do about that.
Okay, I think Edward has a question.
May I address the question?
Yes.
So I would like to present the problem first. So you specified that the protection of the crew member, the radiation protection of the crew member would be made out of tungsten or uranium that has no more neutrons that send the radiation. So my concern is that you have to make at least a layer of at least a couple of tens of centimeters in order to make a viable protection for the crew, so that gamma radiation could not penetrate the layer, so the crew would be safe. But that layer of tungsten is a very dense metal, would increase the weight of the materials that you have to bring on Mars. So how did you organize to settle this problem in order to have a protection for the crew and also have your weight, your materials in the weight limit?
So we actually talked about this earlier in the presentation. I think if you look on the recording, you can see that. Yes, it's heavy. You're way overestimate for the for 10 centimeters. It's a little lower. Yes, it's very dense. You're right about that. We won't have a square meter though. And all of that weight is included within the kilo power design. It's all been calculated, not by us, but by the National Aeronautics and Space Administration, which is the United States' spaceflight and aeronautics branch. And it's 1,500 kilograms. And that's a weight that we're willing to take. We don't need that much shielding. We need a significant amount, enough to make it safe. But yes, it is heavy. You're right about that. But it's included within the mass. And we're still under the limit. So that's a more energy dense way to power your base than solar. We understand why you might use solar, but in terms of pure energy density, this is higher. So I hope that answers your question. I think if you're still confused, you're welcome to go take a look at the recording of the presentation.
And I'll also add to what Leo said. In terms of radiation protection for our habitat in the material of the habitat itself, as seen as our paper, I think it's about page 9, there's a diagram of the TransHab, which was like a prototyped idea of an inflatable Mars habitat. And we're planning on basing our habitat's material layering off of that. And that is for the exact purpose of the TransHab being able to have a lot of radiation protection. I hope that answers your question.
I would also just like to add to that the questions that AstroMineX is asking are a lot of hypotheticals, and as we addressed at the start of our presentation for the rebuttal, that these hypotheticals can apply to any mission, even AstroMineX's own mission, and so these should not be considered from that standpoint as well.
I don't think it's hypothetical when you have a nuclear reactor near some crew members, when you have a limited of radiation that is calculated per year, and it's about, I don't know, some millisieverts, and near a nuclear reactor, the radiation activity is increasing as you are near it. So
Edward, one second. Can I address Edward's concern very quickly?
Quickly, yes.
Yes. Listen, I didn't calculate the amount of radiation shielding needed to make it safe, okay? And I don't think I should, because for one, there's a much more complicated the orbital mechanics calculation, and a very reputable source did calculate it, and that source is NASA. If you want to, you can go on this, you can either follow the source links in our presentation to go see NASA's official figures, Or you can go on this website and search for yourself called the NASA Technical Report Server. And you can search up kilopower on that, and you'll find tons and tons and tons of scientific papers. You can go on ArcSiv as well, any scientific paper website. And you'll see that with the current radiation shielding design, with, for instance, using lithium hydride and tungsten or depleted uranium, the reactor is more than safe. Now, as a quick question, I've known 1 or 2 nuclear reactor operators, friends of my parents, and they're not dead. They don't have cancer. I recognize that they use a pool of water to shield commercial nuclear reactors, but nuclear radiation shielding is a thing, and it works. And so if you want, go take a look at our sources and see what they say. If you want to dispute with them, email NASA them.
Yeah, thank you. And I also want to mention that one last thing. I know you are very busy. So I think our questions are not only hypothetical, they're actually punctual. And I want to ask you, you will have a mission of 15 months. So the mass of the radioactive the substance that you will bring will be at least some kilograms. Have you taken any account of protection for the nuclear waste? Because so you said a million times that the reactor has protection, but do you have protection for the waste?
All the waste that'll be, so in a nuclear reactor, all the 2-year time frame, all the waste that'll be created will be within the core. Once after many decades, the reactor will be unusable due to all the nuclear waste. You'll just keep it inside the kilopower because, as I mentioned earlier, the kilopower has more than adequate radiation shielding, and so you'll just let it sit there. But that'll be after many, many decades, and after 2 years, for a 2-year Mars mission, that is not considered.
Okay.
About the next missions.
Okay. All right. Anae has one thing briefly to say.
Thank you to all the teams that presented. It was really good to see everyone's ideas. I would like just to end this on a positive note and to say that we, Team Aspera, were put together as a team and we had no prior connections with each other. And despite the time differences and a lot of dramas that we had down the road, we worked from a place of respect, and that has seen us with this finished product, which we feel is pretty good, and that we've done to the best of our abilities, and a design that is balanced and feasible. And I would like to say good luck to all the teams, and I would like to see how we all do.
I think this dialogue has been wonderful. You guys may feel, emotions about the back and forth dialogue, but what you're doing is important. That part is the most important. And I love that you're thinking so deeply about this project and so passionately that you're literally picking apart each other's projects. This is exactly what happens in calls and meetings in NASA, ESA, JAXA, all of the space organizations. They do this over and over and over. And sometimes they have screaming matches because they think their research is the best. They think their idea is the best. And so this is how we move things forward. Discussion, questions, answers, making people, the whole point of science is to make people question whether or not their ideas and research is correct. So you can't just have an idea and do it. You need other people to go back and forth with, just like we're doing. So I love this dialogue. This has been wonderful and amazing. You guys are doing a great job. It makes me confident for the future of humanity that we have so many bright young students who are so passionate. And that's why we do these competitions. If anybody has any last thing to say, let me know. I am proud of all of you. You've all worked very hard, and this isn't an easy competition. Dr. Robert Zubrin and the other judges will get copies of your papers and all of these recordings. And I believe we're scheduled to announce the winner July 29th. give us some leeway on that because we also have our convention starting August 8th. So things might be delayed a little bit because of that. So that's the plan. So just be a little patient with us while we get all the judges together to grade your papers and presentations. Is there anything else from anyone?
I would like to say some words. So we as a team, AstroMineX, we would like to thank you for letting us present our ideas and letting us expressing our opinions and having debates with other people, which will help us in the future.
Yes.
We would like also to thank to other teams, especially Team Aspera, for having some interesting debates, which usually we don't have the opportunity to have.
Yes, it's great to see another perspective. It makes you think more deeply. Wonderful.
We'd like to say the same.
Thank you. You've all done a great job. I look forward to seeing you all in the future, and I will be sending this recording out to you hopefully today. I have several other meetings today, but hopefully this will get out to you today. And thank you to the mentors, Shreya and Peyton, and all of our judges who are unnamed right now for privacy. And all of you students, great job. I look forward to talking to you again very soon. Thank you, everyone. Have a wonderful day. Bye.
Have a
Bye,
wonderful
thank
day.
you.
Have a
Goodbye.
nice day. Bye.
Bye.
Bye-bye.